I'm Ivers Peterson. I'm the Director of Publications at the MAA. And it's my pleasure to introduce the lecture tonight. Math Awareness Month was April, and the theme was mathematics and sustainability. That month is over, but this continues to be the year of the mathematics of planet Earth, a year-long celebration, and awareness raising of those kinds of issues. So this talk is both a continuation of Math Awareness Month and an extension into the rest of the year of the concerns that we all have about Earth and the use of mathematics to solve some of those problems. Our speaker tonight is Charles Hadlock. He is a graduate of the University of Illinois in mathematics, but he took a somewhat unconventional career path. He worked for a consulting firm and got to wander the world looking into, risky situations of all sorts. Chemical plants, underground mines, all kinds of different areas, and he may actually fill you in on some of the places that he's personally been to that involve these risks. Took another somewhat risky position when he became dean of the business school at Bentley University, and did that for a number of years, and now he's a professor, but not of mathematics, but something much broader, and my impression is freer, so he can do almost anything he wants in his classes and courses. He's also an author for the MAA of a number of books, going back to field theory and its classical problems. This will give you a sense of his range of the kinds of interests he's had over the years. This actually won the Beckenbach Book Prize as an outstanding MAA published book back when it was first published. A very well-regarded book on mathematical modeling in the environment that we published. He was editor of a series called Mathematics in Service to the Community, a series of papers on learning experiences and how they can be used to help in communities. And then his newest book, which is just out, published by the MAA, called 6 Sources of Collapse. And I suspect you'll be hearing a little more about this book from today's talk. Again, drawing on his many years of experiences, looking at all of these kinds of issues in all kinds of different ways. So, Charles Hadlock.
Thank you very much for coming tonight. Number one, because by your coming, you reinforced my idea that this subject is important. I think we all know that sustainability is a really big issue facing our society, and I pair it together with collapse because the collapse of the environment is closely tied in with the collapse of or the changeover of institutions, of countries, of governments, of all kinds of things, and so I think it's a very important topic. I originally thought that you probably all came because of the importance of the topic until I noticed the enthusiasm with which everybody was going through the free book pile out there. And between the free book pile and the refreshments that we had, I realized there are multiple motivations for coming. But I'll be optimistic, and I'll think that you came because you agree with me that this is a very important topic. I know that this is a very learned audience. I know it's a diverse audience. People from different fields are here. I hope I have something for everyone, but I'll have some things that are probably of greater interest to some than to others. But I'd like to start, if I have a group of students, I like to start by giving a quiz to the audience. I would not go out on a limb by trying to give a quiz to this audience. But if I were to give a quiz to this audience, I would ask how many people in the room know the story behind the picture that's on the screen there. And, I'll take a show of hands. All right, let the record show that it is not a majority of the people in the room, right? Let the record show that even with a very distinguished audience, there's not an overwhelming number of people who can tell me the story, represent a very famous story, represented by the picture on the screen here. And I was giving a talk a few weeks ago out in the Cincinnati area to a university audience, and I asked the same question, and only one hand went up there, and that was, in a way, an embarrassment for the people that live in Cincinnati, because this story really revolves around Cincinnati, because this passenger pigeon here, whose name is Martha, it was the last passenger pigeon on Earth, who died in the Cincinnati Zoo on September 1st, 1914, and is the end of a horrific story of how successful we can be at obliterating species and changing the environment. And there are many lessons to be gotten from this. In fact, with the passenger pigeon, to summarize the story briefly, that was probably the most prolific bird on Earth. There were probably billions of them, maybe about 4 billion inhabiting North America. They used to inhabit Michigan, Pennsylvania, in the wintertime, northern New York, and then migrate to the south, it should be in the wintertime. And when the flocks would go overhead, there wouldn't be 1 million birds in a flock. There might be 100 million birds in a flock, or maybe 1 billion birds. And there were stories written about how the skies went black for hours as the passenger pigeons went overhead. Now that's just a couple hundred years ago. And now there's not a single passenger pigeon. Now I can understand how you might eliminate the rhinoceros, or the elephant, or the woolly mammoth, the bison. I can see big animals teetering on the brink of extinction because they're not as mobile and they don't exist in the same numbers that the birds do. But try to explain how it is that even if we are very efficient at killing, which we are, how is it that about 4 billion birds were absolutely wiped out from the face of the earth? And it was an interesting question, not yet fully solved, in my opinion. And we'll come back to that, and we'll come back to this issue a little bit later on. Now, as Ivor said, I work in the environmental field, or I have worked in the environmental field, mostly on in the consulting industry, and then writing about it more when I came back to academia. Working in the environmental field, people frequently say, what's a mathematician doing writing books on the environment or working in the environmental business? It happens all the time. I get this question over and over again. And people expect it might be a biologist, a chemist, an engineer, something like that. A mathematician leading the charge on some environmental issues. And my answer to that is that there is no better field to come from, to work in the environment, than mathematics. And the reason is this, that questions about the environment invariably are quantitative questions. They're invariably quantitative questions. Whether you're talking about the dynamics of change of the size of the population of passenger pigeons or something else, or you're interested in what level of pesticides cause what level of damage to a population, or you're interested in the probability of a catastrophic accident at a major chemical plant or a nuclear plant, and what the consequences of that would be on the surrounding environment. They're all quantitative questions. Until they become quantitative questions, they're kind of murky things that people are allowed to have different kinds of opinions about. But they eventually, when you get quantitative about it, because you have to issue regulations or make decisions or make investments, when you get quantitative about it, mathematics has to enter the picture. And my view of mathematics is that it is the integrating field. It takes the input from all these other relevant fields, whether it's biology, chemistry, economics, physics, engineering. It takes the input from these different fields and it creates a structure so that you can balance one factor against the other and you can make good decisions about how to manage the environment. So for me, being a mathematician working in the environment is very, very natural. But I'm so tired of answering that question that I I carry around a business card that doesn't even give a hint that I'm a mathematician, because I don't know how many. I know there are quite a few quite distinguished mathematicians in the room here, but I find anytime I tell somebody I'm a mathematician, they kind of back away from me. I mean, unless it's a group of geeky people, and so I have this oddball title. When I decided I wanted to get out of being dean, I created a title. I won't even bore you with it, because you couldn't understand what it means anyway, but it lets me do anything I want, which is what I just said, and so it makes me a very happy academic. Now, here's the bottom line of what I want to say today. That collapses, whether we're talking about the environmental field or any other field, that collapses consistently show certain kinds of dynamics. There are different kinds of dynamics that show up over and over again in many different collapses. Whether we're talking about a positive collapse where you're trying to kill a tumor, or trying to eradicate polio, or trying to bring down the Soviet Union, or bring down a drug network, or whether they're collapses that we're trying to avoid, like gross changes in the environment that would be extremely disruptive, the collapse of an economy, the failure of a nation. If we look at the collapses over this wide spectrum, we find, I think, certain commonalities. And many of these common features, which are what I call the 6 sources of collapse, I don't say the 6 sources of collapse, I say 6 sources of collapse. When we find these common features, many of them can be understood better if you use some simple mathematical models to really get into your head how much these things can contribute to rapid change, breakdown, and collapse. So what I want to do today is give you an introduction to these 6 sources of collapse, a brief introduction to some of the kinds of mathematics that are involved in modeling them, just in a brief introduction to show you something about the range, and then I want to argue near the end that when we look at an individual collapse, whether it's the collapse of the dinosaurs or the passage of pigeons or long-term capital management or Somalia, when we look at collapses, there's a lot to be gained by looking at them through multiple lenses, through as many of these 6 dimensions of collapse, because the different ways of looking at collapse give us different insights into how it unfolds and how we can manage it for the future. So that's my plan for the talk here, if that's all right. And just a reminder, of course, that collapses all around us. Just in a single day, looking at headlines in newspapers, I picked up these. It's all over the place. The melting of the ice in the Andes, or in the Pyrenees, or almost anywhere else. Pot garden poison threatens predator extinction. People growing pot in the Pacific Northwest trying to poison rats. So the rats don't eat the pot plants, but by poisoning the rats, what happens is that the fishers, which like to live off the rats, fishers, or people call them fisher cats, they were threatened with extinction because they're eating rats that had consumed the poison. So we see the propagation of these things through the environment and through the ecosystem. The economic collapse in Cyprus, and imagine similar situations in a much larger country. The level of disruption that we could have, and what if Social Security were to collapse here? I mean, do you think people would just sit around and twiddle their thumbs? What would really happen? The extinction or the collapse of products like the PC, the collapse of fads. You don't see CB radios anymore; they collapsed, right? You don't see hush puppies anymore. They came back for a while, like Malcolm Gladwell pointed out the tipping point, but they're gone again. They collapsed a second time. You look at cities now collapsing under debt by paying off pension funds, and then who knows what's going to happen in North Korea, though maybe there were some good signs in the last couple of days. But these were just a few headlines that I thought would remind us all of the scope of potentially sudden change existing throughout the world. Now, most of the people in the room here are on the older side, and you've seen lots of change over the years. Younger people haven't seen quite so much. So to them, things look like they're, kind of going along. But if I compare the geography book today with the geography book I studied in grammar school, or with the atlas that I inherited from my grandmother, I'm aware of the fact that gross changes in the world map, for example, right? Things really change. Countries fail. The United States will collapse. I don't know whether it's going to be with a bang or with a whimper, but we're not going to last forever. So we have a change going on, sometimes sudden, sometimes not, but we'd like to do it. We'd like to let these things unfold in ways that are not too disruptive and in ways that we can manage. So here are what I call the 6 lenses, the 6 dimensions of collapse that I'd like to spend a little time talking about here today. Low probability events. Okay, you can probably all think of examples, but I'll give you examples as we go, so I won't belabor these right now. Group behavior. Okay, a whole bunch of people running off in a certain direction and doing something maybe irrationally and causing some disaster to occur, or maybe something else. Gains in evolution, the evolutionary processes, and game playing, which is really what evolutionary processes are. Another phenomenon, another dynamic that I find in a lot of collapses. Instability, common source of collapse. Nonlinearity in its many, many different forms, common source of collapse. Somewhat different from instability here, but frequently I'll talk about these two together as the dynamics of the system. And network effects. If I were a young person going to graduate school these days, and I like quantitative stuff, I would say go study networks. Because there's a lot of action right now in the field of networks, understanding networks better. So these are the 6 things, the 6 themes that I've organized some of my examples around. Let's take a look. Low probability events. The one on the top, you see a lineman lifted way up in the air on a bucket truck with a long pole lifting a deer carcass off a power line in Missoula, Montana, because it caused a power outage in Missoula, Montana. That's an interesting thing, isn't it? Murphy's Law says that if something can happen, it will, and this says if something can't happen, it may still. Right? Anybody know how that happened? Okay, it was dropped by an eagle. It's a small deer. It was dropped by an eagle. Interesting, right? It just expands your imagination. Okay. Now, this is an interesting one here. It's not a great picture, but it's the best one I can find. I worked for a long time as a consultant for the Environmental Protection Agency that had been charged with setting regulations for the disposal of high-level radioactive waste. And one of the options that the Department of Energy had proposed was to bury the waste underground in caverns in salt mines, possibly abandoned salt mines, possibly caverns created for that purpose. And there are salt mines along the Gulf area. There are ones elsewhere in the country, in Michigan, in New York, in the Southwest, in a number of places. And one of the things that we were concerned about was the possibility of future human intrusion. Could people possibly drill into one of these things in the future and start bringing radioactive material to the surface? Maybe 500,000 years from now, okay? Maybe after the topography had changed some and people didn't realize where things were. And we took a lot of heat for our quantitative estimates of the risk of that occurring. We found all kinds of examples of people drilling where they shouldn't drill. But to specifically investigate the Gulf Coast region, with the support of the EPA, we took a helicopter out into the Gulf and we landed on a drilling rig and a production platform down there. We talked to a lot of people in the industry and asked them, what is the chance that you're going to drill into one of the salt mines that's along the coast here? And we understood how they worked, we understood how they laid out their maps, and we understood that people in their headquarters had perfectly accurate drawings of everything. And we were told the probability was 0 that that could happen. And then we went down into some of the salt mines down there, and we put the same question to the salt miners and to the management of the mining companies. You really get different opinions when you talk to the management and you talk to the workers down there. And I've done a lot of this kind of stuff around the world. You get totally different answers from people. But basically, the consensus of the people in the salt mining industry was, look, they know where they are, we know where we are, we have accurate maps of where our mine goes, they're not going to drill it, this is a stupid thing to worry about. Then I think it was November 1980, this happened. This used to be a lake here. You're watching something like Niagara Falls here. This had been a lake up at this level here, and a Texaco drill rig put a 12-inch hole into a diamond crystal salt mine in Jefferson Island, Louisiana. And it started off as a 12-inch hole, but in fact, as the water went shooting down the hole, the thing got so big the drill rig disappeared. It's never been seen again. Half a dozen barges went flying down with it. There are a few fishermen on the lake racing to the shore to the other side because the current was going down the hole. And of course, you can imagine the people in the salt mine didn't like this either. They're racing to get out, but shooting up the shaft there. And it's a miracle that nobody was killed. But here we are, assured that the thing couldn't happen. And it happened right. It didn't happen 500 years from now. It happened with an operating mine underground, and they did. And of course, here's the Fukushima nuclear disaster with a tsunami, which, in my opinion, should have been something the plant had been designed for. And you see it totally wiped out, and its backup systems wiped out by the tsunami. And we all know the magnitude of the disaster that has resulted from that. Now, I don't want to go into all the different kinds of ways that mathematicians can help estimate these low probabilities. But I do want to tell you first that we, as a society, do a poor job of estimating low probabilities, and we have a variety of tools around that would let us do a better job. And I just wanted, in passing, because we have a number of mathematical people here, and I wanted to remind you of something that it leads to a lot of problems in this business. There's mathematicians and there's statisticians, and when you read statistics in journals, sometimes they say, oh, they're always assuming normality, they're always assuming this, and they seem to get away with it, but it's so frustrating because as mathematicians, we know they're making assumptions of things that may not really be true. But I want to tell you about something maybe you haven't come across before. This you have come across, many of you have come across, called the central limit theorem. It says, this is why statisticians get away with murder. You could start with any old probability distribution, not a normal distribution, some weirdo distribution like this exponential distribution. No, it's not a bell-shaped curve or anything. But if you take samples from it, and you take the mean of each sample, and you take another sample, and you take the mean of that sample, you look at the distribution of the means of the samples. If the samples are of size 10, already it starts to look like a bell-shaped curve. The samples are of size 25, it looks a little more like the bell-shaped curve. And so the distribution of the means of the samples looks like a normal distribution, even if the original distribution is some weirdo thing that doesn't resemble a bell-shaped curve at all, right? That is the saving grace for people that do loose statistics, okay? But there's another theorem. There's another theorem that's not widely known among people that study statistics that I wanted to call to your attention. And so it's the parallel of this. It's the reason I put this up, not just because it's fun to knock statisticians. Here I have a distribution, another distribution. It's not a normal distribution, it's a Cauchy distribution, doesn't matter, okay? And what I'm interested in is looking at the maximum value of each sample, not the mean value of a sample, but just the maximum of a sample. And so, for example, if I took 10 picks out of this distribution, I took the maximum, and I took another 10 picks, and I looked at the maximum, another 10 picks looked at the maximum, and I did a histogram of those, and I took more and more and more of them. They actually follow this curve here. If I took 20 picks, and I looked at the maximum of 20 picks, you know they're going to be higher. Because if you take a 20 things from a sample of size 20, the largest of the 20 is going to, in general, be larger than if I just took 10 things, right? So you know that the largest of each 20 sample is going to be bigger than the largest of most 10 samples. And if I did a histogram of all of those, that would be the case here. Okay? All of these curves, even though they gradually go over to the right, they really all have exactly the same shape. They can all be normalized to a standard distribution called the generalized extreme value distribution. And that's the kind of distribution we use when we try to estimate the max of the 100-year flood, the 200-year wind, the 1,000-year asteroid impact. When we're looking at the maximum value of something, we use the generalized extreme value distribution, and it's a very interesting and well-accepted way for developing the basis for some kinds of risks of low probability events. What we find in general when we use these things is that these distributions have heavy tails, which means that out to the right, the probability of things occurring is greater than if we took our original data and we modeled it with a normal distribution. Significantly larger than if we model it with a normal distribution. And it's really the difference between the extreme value heavy tails and the normal distribution heavy tails that really makes a difference sometimes in the kind of risk estimates that people use, whether it's in engineering or in finance. And we'll see a spectacular finance case a little bit later. Let me go on. That was low probability events, but here's group behavior. Let's just let's see. This is the one I like to stick in front of my colleagues in the finance department, and my son, who's a professor of finance as well. Here's somebody that says he thinks he has a stock that could really excel. Hey, really excel. Excel, sell, sell, sell. All right, they're all selling. All right. They're going crazy. So this guy says, "This is madness. I can't take it anymore. Goodbye. Goodbye. Buy, 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 buy." Well, now they're all buying. This is group behavior. It's not just a joke. It really happens. Okay? I mean, maybe it doesn't happen quite like this, but I love this this cartoon from Cartoons because it captures this. Because in the world of finance, this causes real problems. When everybody starts investing the same way, the probabilities of the market start to change. And we get heavy tails where we wouldn't have heavy tails if people were operating independently. So it changes the whole dynamics of things. Well, now we have lots of different ways in which group behavior can occur other than in hypothetical disasters like this. But even I take a simple example here. It's not a collapse, but it's a way of modeling group behavior. Look, birds fly in flocks. Fish swim in schools. We see many examples of group behavior, sometimes simple like that, sometimes much more complex. And I thought I'd show you one thing, because again, it's something that people don't bump into that often. Here I'm starting out with a whole bunch of birds. I'm going to let them fly around randomly. And let's see what happens if I build a model of this. Might take just a second for this thing to open up. Let's see if it works. It does. Okay, so I'm going to play God and say, let there be birds. All right. Now, here I have a whole bunch of birds here. They're all moving around independently. They're kind of like little triangles. You can see which way they're pointing. Okay, and I have certain rules for them as they move. They don't want to bump into each other. They kind of want to go in the same direction as one's around them. And so I could use this to test out different theories about what is it that causes birds to fly in flocks. I mean, if it was the army, you'd know there'd be somebody up there yelling at them saying, "Come this way," waving the flag, right? But there's no bird up there waving a flag saying, "Let's everybody go this way." But they still all seem to do it, don't they? So to investigate that kind of group behavior on a simple level, let's just let them fly. And if they're going a little too slow for us, we can just make them go faster. Let's see what happens here. I have a toroidal geometry here, so if they go off the left, they come back in the right here. And the same for the top and the bottom. Here we are. We're getting some flocks of birds. And, I offer this only as an example. I'm going to talk about it a little bit more in a second, about a way of capturing group behavior where the different members of the group are all acting on their own, but they have certain principles of action. And we put them all together, and we look for what we call the emergence of certain patterns of behavior that we might find in human civilizations as well as in flocks of birds. But
the birds are doing pretty well here. So there's a good chance we're in the right ballpark in understanding the kind of principles they might follow in flying around. Let me leave that for now. This same approach has been applied by some people at the Brookings Institute. I see one of my former students at the Brookings Institute has come in here, and very interesting work by Robert Axtell and Josh Epstein, who built using this technique, which is called agent-based modeling, or the individual birds flying around called agents. And agent-based modeling is used all over the place now. But they built an artificial society, starting with agents that were just trying to migrate between one source of food and another source of food. They were kind of going around. Then they had two kinds of food, sugar and spice. Then they could trade, and then they could marry and reproduce, and then they could leave an inheritance. They built a whole economy around these agents, these individual agents, and they explored different rules and different principles for how a human society might function. And it's absolutely fascinating. This book was done, I think, in the early 90s, and still is a very interesting thing to read. And then somebody said, well, now, all right, you did a great job at artificial societies here, but what about real societies? So they got together with a very distinguished group of anthropologists, historians, geologists, climatologists, and they went to investigate the Longhouse Valley Anasazi in the southwestern United States, the Pueblo-type Indians in this Longhouse Valley. And the question really was, could the environmental changes that occurred there a few centuries ago, could they explain why that society collapsed? And so they studied the amount of agriculture that could be supported. They studied how people organized their households, how they had places they lived and places they farmed. They built an agent-based model for that society. And they determined the environmental forcing conditions, which they could learn, they understood pretty well from studying pollen and the like, that was not sufficient to cause the collapse of the society. It was a very well-received scientific investigation published in the Proceedings of the National Academy of Sciences, and another interesting model of group behavior, how this whole society functioned. But let me go to my third subject here, games and evolution, because that's another world still. We live in a society where we, on one aspect we compete with each other, another aspect we cooperate with each other. One species might compete with another species, but also cooperate with other species. We live in a mixture of cooperation and competition, which is what I constantly am telling my game theory classes. And sometimes this competition leads to significant changes in a changing environment. For example, it's generally it's well known that we probably had 5 major extinctions of species in the history of life on Earth, and I would say that most people whose work I read say that we are in the midst of a 6th one, and it's being caused by us. It was probably the 6th major extinction in the history of the Earth, and the number of species that are disappearing is huge because we're changing the whole habitat of the Earth. So that's certainly not a surprising fact. So we try to understand this competition and the like, and one way that we can do that is through game theory. Now, let me. I know we have some experts in game theory here, so some of what I'm going to say is very familiar to you. But let me just run through this briefly. Let's suppose we have 2 prisoners, Bonnie and Clyde, just been captured by the police. The police think they have committed a burglary, but they don't have any proof of that fact. They have, however, found that Bonnie and Clyde are carrying guns that they're not authorized to carry, if that's still allowed these days. I don't know. And so they take the two of them off to two separate interrogation rooms, and they try to make a deal with them, just like they do these days. They say, look, if you rat out the other person, we'll give you a good deal. If you confess and basically rat out the other person so we can put them away, we'll let you off the hook. If you both confess, well, we don't get as much good out of your confession, so we'll almost let you off the hook. And if you both keep quiet, the best we can do, we're going to get you on a gun charge. So, right, there's different outcomes. So one of them could rat out the other. They could both confess. They could both keep quiet. And if I change those outcomes into numbers here, where a higher number is more advantageous, look, for Bonnie, the best thing is to confess, and especially if Clyde doesn't, especially is to not confess, is to confess if Clyde does not confess, if Clyde cooperates, and then Bonnie is going to get off, and Clyde is going to get sent off to jail for a long time. 0 is the worst outcome for Clyde. So we have this game where this ordered pair gives you the outcome for Bonnie and Clyde, is called Priz's Dilemma. And if you look at it carefully, each player is always going to do better by defecting. Okay, each player is going to do better because Bonnie is going to get a 5 or a 1 instead of a 3 or a 0 by defecting. Clyde is going to get a 5 or a 1 instead of a 3 or a 0 by defecting. Whereas they would both do better. The best outcome in general for the two of them would be to both keep quiet. But the logic of the situation drives them to a less than optimal way of proceeding. Well, a political scientist at the University of Michigan has made a lot out of this model. In fact, there's thousands of papers written on Priz's Dilemma. But this fellow, Robert Axelrod, decided to see how real people would play this game. Now, I'm telling you about this because we use this to model evolutionary processes. We use this to model evolutionary processes. It's very different from the other subjects I've talked about, the group behavior and the probability. It's a different world. Okay? And so he set up a tournament where he was going to play. He wrote to a whole bunch of people who are supposedly experts in game theory and said, all right, send me a computer program for how you would play this game. And I'll play them all against each other and let's see who's best. And he got from mathematicians, economists, computer scientists, psychologists, political scientists, everybody wrote in who was not too embarrassed without a limb. Some of them probably wish they hadn't. And then he tallied up the results of this. And this A strategy here, A strategy, which is called tit for tat, won the game. Some of you, I'm sure, have heard. The tit for tat strategy says that if I'm going to play the game with you 30 times, okay, whatever you do, I'm going to be nice the first time, and I'm going to keep quiet. And whatever you do, I'm going to do it the next time. So if you're mean to me, I'll be mean to you the next time. If you're nice to me, I'll be nice to you the next time. That's the tit for tat strategy. Other people had different strategies. It was, I'm going to be nice, but as soon as you screw me, I'm going to just kill you for the rest of the whole thing. Okay? There's lots of different games. Some people tried to use Bayes' theorem and all kinds of stuff on the past moves and the like to come up with strategies. But tit for tat, interesting, I'll just tell you, it lost to every other strategy, but it won the tournament. It lost to every other strategy, but it came so close to winning that it got a high score against every strategy, whereas when the other strategies were playing each other, they just ate each other up, and they came out with miserable results. So tit for tat won, and won the whole tournament, even though it never beat a single strategy face to face. Very interesting. Right? And the really 4 principles. Let me see if I can remember them. If I can't, my game theory student Edith over there, who was shaking her head, will certainly remember. It's a nice strategy. Okay, it's not too mean. It doesn't start by defecting, for example. It's a clear strategy, and it's easy to interact with it because it's kind of a predictable strategy once you've played a couple of rounds with it. It's a forgiving strategy, If you're mean to me and I'm mean to you, if you go not back nice to me, I'll be nice to you again. It's a forgiving strategy. And what's the other property it's got? Well, that's good enough. The bottom line is that by playing with these strategies, we are really modeling a combination of a cooperative, competitive environment among players, which we can take to the next level then by setting up an agent-based model with a whole bunch of agents running around the field here, and every time they meet, they play Prisoner's Dilemma or any other game against each other, and we keep track of their scores when they do that. But the only difference between the other game and this game is that every little while, I'm going to tally up their scores, and I'm going to kill off the ones that have the lowest scores and replace them with ones that have better scores. In other words, if strategy C is running really poor, I'll kill off half the strategy C players, replace them with, say, strategy A players if they're doing well at that time. In other words, I'm modeling the evolutionary process that the fitness of any one of my agents running around here is given by the score that they've compiled to date in their games against other players. And the ones that are winning have a higher fitness, so they are more successful in moving on to the next generation. And I throw the old ones out and I replace them with new ones. So now, if I play this game, and I won't take the time to do it, I'll watch strategies dying. I'll watch them being replaced with other strategy. That's what this graph is. This was done by one of my students. And I'll see a strategy did very well at the beginning. After the mix of strategies changes, might start to do very poorly. That's what happens in real ecosystems. Species themselves don't evolve that fast, but ecosystems evolve really, really fast. Ecosystems change, and that's what causes a lot of collapse. The business environment changes a lot faster than the businesses do, and that's why a lot of businesses go out of business. Okay? It's a change of the industrial or the technological or the natural ecosystem. In fact, we can even let the agents develop their own strategies, because I can use a technique called the genetic algorithm to actually program in with sequences of zeros and ones the strategies that the individual players would use. And then I can let them actually mate up on the screen here, or maybe behind the screen. I can let them mate, and I can join their chromosomes up here to produce new strategies and see what kind of strategies will evolve over time based on this concept of fitness and evolution. It's a very neat way to model evolutionary processes, and it's used extensively. But let me go on to the next topic here, stability. If I take a book, this is a nice book. You take a book here, and watch what happens here. If I flip it, sometimes I'll offer somebody $20 in the audience, but this is a distinguished audience, so I won't do it. Well, if I flip this book like this, no problem. I can make it spin around pretty well, right? Okay. Now watch. Okay, watch this. Not bad, not bad. The cover comes off, but not bad, right? I mean, it went around the way it's supposed to, right? Okay. Watch this. Whoa. Better ruin the MAA's book supply here. Doesn't work. It's unstable. In fact, there's a picture of somebody trying to do that on this, up in the space station. It's very, very interesting. A space station doesn't collapse. You really watch it for a while and figure out what's going on. Okay, but it's an unstable motion. You think you should be able to flip it around like that. It's unstable. It's like I was sleeping with my wife at this country house we have in New Hampshire where it freezes in the winter, and we got the controls mixed up on the electric blanket. So, you understand what happens when you do that, right? Okay, I'm getting too hot, so I turn mine down. She starts freezing, so she turns hers up. But it's really, I'm starting to spoil now because she's turning mine up by mistake. Away we go. Instability, you know what I mean? Okay? And it applies to lots of things in the world. We're looking at the stability of populations, a lynx and a snowshoe hare, moose and wolves on Île Royale. The Asiatic carp, we're wondering what impact that will have on the Great Lakes, for example. I don't have enough time to really play this Asian-based model here, but this is a big battle between the flu virus and the human population, and they're really competing with each other, and we wonder really who goes unstable and disappears, and what victory really means here. But the point is, stability is a big issue that can lead to collapses. We have some ways of modeling it using traditional mathematics. I don't think this is the kind of thing I want to go into tonight. We have differential equations. We have predators and prey. Now, predators and prey, it could be lynx and snowshoe hares, but it could be fishing boats and cod. It could be people that sell stocks and bonds and customers. I mean, there's different ways of thinking of the interactions between predators and prey. It could be deans and faculty. I don't know what faculty and students are. You can think about all kinds of ways. And the population of one goes up and down, and the population of the other goes up and down, somewhat out of sync with each other. At least in the case of ships and fisheries or lynxes and hares. And there are lots of different ways that many of you have seen for modeling that mathematically. But here's one thing I should say about stability. Would you rather be flying in an airplane that is really stable or really unstable? A lot of people would rather be in a very unstable airplane. You wouldn't think that. Now, here are a couple of unstable airplanes. This one looks unstable. I mean, I don't think I would go into this X-29 experimental aircraft, but even this Eurofighter here is a very unstable airplane. Because look, if you're a fighter pilot, and you just imagine you're trying to swerve out of the way of something coming your way, and the plane really likes to be stable. It just wants to go right straight ahead. Wouldn't be any good, right? You want something where just a tiny little change, and bang, you go flying somewhere else. As long as you can control it to a certain extent. You want to kind of be on the edge of instability here. You don't want to be too locked into too stable environment. And so instability can be good in some circumstances, but it wasn't very good for the Chernobyl reactor, which, if you're ever interested in knowing how Chernobyl really collapsed, an interesting discussion. I really had to research that thoroughly when I wrote the book. I tried to lay it out in very clear terms how the Chernobyl reactor went down. But the whole problem is trying to control instability. And there are two issues involved in this, called controllability and observability. Very common terms to engineers. The observability means you really need to know what's going on at every moment. And controllability means that you have enough power and enough things that you can do to then act on that to bring about the result you want. And in Chernobyl, there were problems both with observability, nobody knew what was going on, and controllability, they didn't have enough control over what they really needed to control in the circumstances. So instability brings things down. Talking about things coming down, nonlinearity also brings things down. We all are always assuming things are linear. When you do the pendulum equation and you say, well, for small theta, sine theta is approximately equal to theta, and you do that in physics, you just run it right by the students, nobody ever worries about it. You're really making a linearity assumption. But sometimes these linearity assumptions, you're assuming something follows a straight line when it doesn't follow a straight line, lead to some pretty big disasters, two of which are shown on the screen here. This one is one of the Liberty ships, the SS Schenectady, which I think it was in January 1943, I think, sitting calmly in harbor in Portland, Oregon, and just cracked like that. I didn't know about that until I started reading about these things and putting the book together. This is the famous Tacoma Narrows Bridge. Many people have taught differential equations, have thought about this. Our understanding of the collapse of the bridge has changed over the years, and now it seems to really be due to a false assumption of linearity and the spring equation. When that collapsed, by the way, as Ralph Agnew said in his differential equations book, I think it was he said in his differential equations book that one of the mayors there said, we are going to build that bridge right back up just like it was before. And then, of course, the mathematician pointed out, yes, and if you do, it will collapse just like it did. Nonlinearity has many different faces. I won't go into them all here. It has this basic ones, the weather. We can't really predict the weather very well. You know, you watch the maps of the hurricanes approaching the Gulf Coast or something, and they say, well, it's going to hit somewhere between Florida and Texas. That's just a few days before. You say, why can't we do better? You can't predict the weather very far out. It's because of nonlinear effects. You have bifurcations. This is why there's no maximal sustainable yield from fisheries. You have the hysteresis effect. That sometimes it's hard to undo things. You can't go back along the same path that you went on. Then you have the butterfly effect. Famous paper by Edward Lorenz from MIT. The paper was called, "Can the flap of a butterfly's wing in Brazil cause a tornado in Texas?" And of course you say no, right? But the answer is probably yes. Because in chaotic systems, very small changes in initial conditions after a certain amount of time can lead to gross divergences in the way systems behave. That's actually why the orbit of the Earth is chaotic. You didn't know that probably. It won't affect you, but about 100 million years from now, you know, we don't know whether the Earth is going to be on this side of the sun or the other side of the sun. I mean, that's the magnitude of the effect from about a 15-meter displacement of the location of the Earth right now. My last category, network effects. Here's a network of the interstate power system. Here's a terrorist network. They look a little bit different. This is kind of a latticey kind of a network. This is a network that has a few very highly interconnected nodes. A lot of things are centered around those nodes. You can see the topology of networks is quite different. That's why I say studying networks, there's a lot in the study of networks. Hot field to go into now. And surprising things can happen to networks. This is the Northeast Blackout, the one that happened in 2003 as opposed to a number of the other ones that have happened. This is an interesting one because here's what happened in Ohio. There was a power line that was carrying a lot of current, a little more current than they expected it to be carrying because one of their generators was out. And you know, when things carry a lot of current, they get hot. Right? That's why houses burn down sometimes because extension cords get very hot. And when things get hot, they expand. So you don't notice it, but you could actually you could easily observe it. The power lines, hanging power lines, when they're carrying a lot of juice, they're hanging lower than when they're not carrying a lot of juice. They expand and contract. Well, this one expanded, drooped down a little further, hit a tree branch, shorted itself out. It blew a breaker, okay? Knocked out that part of the circuit. Knocked out one part of the circuit. Now the next part of the circuit is picking up even more load than it had before. Well, that power line expanded. That one blew out. Oh, then the next one blew out. This is a simplified reconstruction just on a resistor circuit that I put in the book because it's easy to understand based on high school physics, just resistors and battery. But you would think that professional engineers designing the network of power for the northeastern United States would not have a phenomenon like that lead to this big black spot. But we did. So sometimes what happens on networks is unpredictable or not well predicted. Let's put it that way. Here's another one. I want to tell you that even simple networks are very, very interesting. I have this is two ways to get from point A to D by car. I can either go here through across a bridge and through city streets, and then along a riverway, or I go along this riverway and then through the city streets. The speed on the riverways is not affected by congestion, but the speed on the streets is affected by congestion. It slows down if you have more traffic. So the city proposes to build a bridge across from B to C. Now, people would say, what is the effect of that going to be on traffic? Is it going to improve the traffic flow? And the answer is, it's going to make it worse. It's going to make it worse. Worse. Now, I'm not going to tell you why, because I have to leave you with something to think about, but it's going to make it worse, okay? That's interesting. And if you don't believe it, they tried that in South Korea, and they were right. Okay? They actually took out something like that, and it speeded up the traffic. And they did experiments in Boston and New York and found exactly the same thing. So networks are a tricky business. So now when I come down to the near the end here, and I have a couple of examples where I want to show you that looking at collapses really can benefit from looking at them in multiple frameworks. So I'll just mention a few aspects here. And this is what I found when I was in the industrial world and I was investigating accidents, and you try to figure out why something happened, and it's like peeling an onion, because you find the proximate cause of something. Somebody dropped a wrench into something or this or that, but then you find out, well, now why did that happen? Why was it possible for them to do that? And then why was there a training issue? Was there this kind of? You really start peeling away, and you find there's all kinds of things behind collapses, and I'm saying these different 6 dynamics show up as you unwrap the onion and looking at lots of collapses. Here's Fukushima again, low probability event, the tsunami. But why did they use the standard they used for their estimated probability of the tsunami? Or how did they estimate the probability of tsunami? My guess is, and I'm not involved in that case at all, I don't know the details of it, so it's purely hypothetical, but I've seen similar things, that it's group behavior, just like the Shuttle Challenger disaster. Everybody's sitting around the room trying to talk each other into going ahead, even though it's too cold for the O-rings. But they kind of talk themselves into going ahead. Group behavior. I think it's the same thing with their analysis of the safety standard to use for something like the tsunami. But gains in evolution comes into this, because this really represents the evolution of a nuclear technology that has certain inherent flaws in it. This is a GE boiling water reactor. There are lots of different kinds of nuclear technologies. This is not an inherently safe reactor system. I'm not opposed to nuclear power at all, but there are systems that have better safety properties than this. But it's a system that evolved out of business decisions, competition, and the like. It really came out of an evolutionary process. This is what evolved. This kind of plant evolved as one of our main nuclear options. For better or worse, it's the way things evolved. And we can understand it a little bit in an evolutionary sense. And if we do that, we might be more careful about some of the decisions we make about other technologies that we adopt. Because it leads to the situation where we have a spent fuel storage pool here in each of these units that requires active cooling, constant active cooling, or the spent fuel will melt down, and fission products that have accumulated in the spent fuel will get out into the environment. So it's an inherently unstable situation where we require active efforts to keep it from going unstable or going into a dangerous situation. It's a nonlinearity in the sense of hysteresis. We adopted this nuclear technology. It's hard to turn back. And the network effect that I see in this one is they assume that if all else went wrong, they'd be able to bring in power from the network outside to provide cooling for the plants. And what happened? They lost the outside network, and they didn't have that available to them either. So all these different aspects come into these and many other cases. I talked about the passenger pigeon one before. Let me go on and say something about the financial side of things. You can tell which part of the graphs here I'm interested in. This is a very famous case, LTC at Long-Term Capital Management. The company started up with 2 people who were about to win the Nobel Prize in economics and have won the Nobel Prize. This was really the catch-me-out of hedge funds. Everybody wanted to be a part of this. And as the hedge fund got bigger and bigger, in order to maintain their profitability, they had to borrow more and more money to leverage their investments. Their whole investing system was based on very small margins, so they had to borrow a lot of money, which is called leveraging, in order to accumulate the same kinds of profits they had at the beginning. And what happened is they got so big that they were starting to control the market. And when there was a common cause failure, they were assuming everything was normally distributed, not fat tails to their distributions of things that could happen. But there was an Asian financial crisis in 1997, Russian ruble collapse in 1998, changed the financial picture around. It's a common cause failure. It screwed up everything for them, and they had to start selling their stuff. And because they were so leveraged, when they sold their stuff, that brought the price of the market down. Then they had to sell into a worse market. Nonlinear feedback effect. And the whole system crashed. In May of 2010, in a span of 15 minutes, the market it's in S&P minis, but it affected the Dow Jones. This could be a graph of either one. Crashed because nowadays people don't trade stocks with people, and firms don't trade stocks with firms. Computers trade stocks with computers, and they do it in milliseconds. And a company can do it in 10 milliseconds instead of 15 milliseconds. Can take advantage of those 5 milliseconds. Take advantage of a profit opportunity before somebody else can. That's where they're moving all their computers closer to the exchanges to save on the time it takes for the information to travel. I mean, it's amazing. So you have all these high-speed computers battling it out over these networks, and we think we have them programmed so that they do what we want them to do, but we don't. Because, for example, here, in a span of just 7 seconds, Accenture, a respected firm, its stock price went from $30 a share to a penny. 7 seconds. Apple was selling for $100,000. People were buying it at $100,000. No, people weren't buying it. Computers were buying it on behalf of the idiots that commissioned the computer to buy it. So, network effects, instability, the whole thing went unstable. I mean, these phenomena show up really essentially everywhere. I said at the beginning that some collapses are beneficial, from our standpoint at least. Collapse of the Soviet Union, collapse of polio, collapse of criminal networks, collapse of tumors due to understanding the network of blood flow to the tumor. A theory that Judah Folkman had been derided for many years, and then it turned out to really have been right about. And I could take you through some of these same phenomena through these, but my time is limited and I won't do that. Because I want to get to just the bottom line, which is my last slide, and that is that really the most important aspect of managing prospect collapse is to understand the diverse dynamics that lead to it. And I really believe that mathematics is the best, or at least is an outstanding, organizing principle, and that we should be sharing these kinds of thoughts with our students and our colleagues because we're dealing with a very, very important subject. Thank you very much.
A few minutes for some questions, but I do want to put in another point before. The book, The 6 Sources of Collapse, is available through the MA store online, and it's available as an electronic book through our ebook store also. So look it up on our website, on the MA website, ma.org, and you can take a look you can see the book there. So
it's not heavy-going mathematics. Okay, that's what people frequently assume. I didn't know whether to put mathematics in the title. I have a subtitle. It says, A Mathematician's Perspective on How Things Can Fall Apart in the Blink of an Eye. But I don't think, aside from graphs and the like, you don't need a lot of mathematics. If you have a lot of mathematics, you'll see further insights from it. Yes?
In the heyday of catastrophe theory, it was claimed that would be the key to understanding these kinds of things. What role does catastrophe theory play in your perspective of how to analyze these things?
I think that, I remember the heyday of catastrophe theory, and because it just sounds so sexy. I don't think it ever lived up to the promise that people really ascribed to it, because it really is an investigation of certain kinds of nonlinearities. For example, the bifurcation point that I talked about is a catastrophe. So I think it's, as far as my understanding of catastrophe goes, it's good in certain areas, but it's not the big picture of things. Just like chaos theory. Chaos is another kind of nonlinear dynamical behavior, right? And and it has, and understanding it is important. It gives you a greater appreciation for nonlinearity. But again, I think at certain points in time, maybe chaos theory was oversold. I mean, I could be wrong about that. I may get attacked for saying that. I'm looking around the room, I'm a little worried. Okay, but at least I think that it has its place, but it's one of a number of tools. Yes.
What you have up there would be wonderful, but the key word is diverse dynamics, right? So that's the problem humans have, because most things are caused by black swans.
Well, I mean, black swans, low probability events, and black swans have been found to exist. So, unlike, just like my deer on the power lines, you can estimate low probability events better than we sometimes do. Okay, black swans aren't totally mysterious things. You can. There's extensive data, for example, in the nuclear industry, on human behavior in operating plants and through fault tree methods and proper appreciation for common cause errors, you can estimate the probability of different kinds of major accidents involving plants. Now, at one time, you might have called some of these errors black swans that you couldn't do anything about, but in fact, a great deal of progress has been made. You take the Bhopal accident in India, which was really caused by a disgruntled employee who was trying to destroy a batch of product rather than cause a major accident. And he'd always been told, don't ever let water come in contact with this product here. And so he connected up a hose into a pipe to send water into the product. You can say on the one hand, well, how would you estimate the probability of that? But in fact, when you design a plant like that, you go through a very systematic, you should go through a very systematic procedure, really driven by mathematical structure of looking at different failure modes, and this kind of thing would have turned out in that plant, because we've done it for lots of other chemical plants. So I think you can make a lot of headway on black swans. I think an appreciation for, I think that tsunami could have been better estimated. Now again, I haven't investigated that case myself, but I'm shocked that kind of tsunami was not built into the design basis of the plant. And you can use extreme value statistics for things like that, because we have a good understanding of tsunamis and a long-term geologic record of retracing tsunamis. So you can make pretty good progress on many of these things. You can also design systems so they are less subject to instabilities, so that even if something unexpected really happens, they are more robust in their response to it. So I think an appreciation for instability is good. Now, I've carried out a number of audits of companies and plants in places, and that's the kind of question that you always have in mind when you're helping to look at future risks that companies might be up against. Sometimes the company gets so wrapped up in one kind of risk that they totally forget about another one. They might be very wrapped up in the change in the business ecosystem, right? The business climate change. I just use the word ecosystem because it's really what it is. They might be wrapped up in that, but not thinking all about what about the impact of a low probability event, an economic event, a political event, a military event. In good risk analysis, and good risk analysts constantly remind their clients to really keep these different areas in mind. It's kind of a checklist when they're doing their planning and when they're understanding their risks. And I think that risk analysis has done a lot to do that. Yes.
Do you know Jared Diamond, and does he know you? You must know he wrote a book about it.
No, I love his stuff. I've learned so much from reading his material.
He has a book called Collapse.
It does. Now that's about the collapse of a lot of human societies in different places. It's a fascinating book. A few of his cases are a little bit controversial. I swallow him hook, line, and sinker. I'm not an ecologist, but I've learned so much from his books. And Guns, Germs, and Steel goes really way beyond just that to really understand bigger movements and changes in the
Yeah,
whole
because
human
if the
population.
two of your insights were to be combined, I think it would.
Yes.
Have you looked at the predicted collapse of the global economy as detailed in the Club of Rome report?
No, I think that's something something to worry about. I mean, I haven't really looked at that. I worry about the collapse of political order. I worry about the fact that we have a political system that no one would characterize as ideal. You know, with the case of the passenger pigeon, there were movements to save the passenger pigeon. There were movements in a number of different states that said, look, we have to stop. I mean, they had like giant volleyball nets on the tops of mountains to catch these passenger pigeons. They had buckshot in cannons that they would shoot at the flocks of birds to bring them down. But there were some people who said, look, we can't stop doing this because we're destroying this whole species here, and it went nowhere politically. There were acts in different state legislatures went nowhere. Now, does that sound familiar? I mean, right? I mean, so we, from my standpoint, our political system may be adequate for today, but it may not be adequate for tomorrow. Look, how many companies are democracies? You know, I don't want you to run me out of the room here by taking on democracy, but I don't know any companies that are really democracies. Whether you think about the workers or you think about the shareholders, they're not really democracies in the sense that our government is, right? Because if they were, they probably wouldn't be able to compete. Right? Now, now going on the stage of nations, we've been doing fine because we can afford a lot of inefficiency in the way we do things. We're so powerful and the like. Whether our form of government will work in a more competitive world where everybody has the knowledge and the technology of the United States, say, I don't know. It's a wide open future.
Yeah, I found your comment about the virtues of instability in an airplane really novel to me, anyway. Is that really part of the design
Yes.
of the military aircraft?
Yes. Yes. I mean, maybe there's an aeronautical engineer in here, but these planes are characterized as unstable. Right? They require active control constantly to stay going where they're going. Okay, as opposed to what would be a stable airplane, where if the pilot has a heart attack, at least it's going to go along a while. They're much more on the edge of instability in the sense that they require this active control, and if you just deviate a little bit, you can go in funny ways. But it makes sense because you want to be extremely maneuverable, right?
Do you know when that was put in? That seems like a novel idea.
Yeah.
Can anybody clarify that, Jim? Can
Yeah,
you?
the F-16 was the first unstable fighter aircraft. It produced higher performance, higher maneuverability than the previous ones. All the ones before that, the F-4 and so on, they were all stable. All passenger planes are stable.
It's so interesting, isn't it? I didn't know that until I got into this business here. It's a fascinating case. Yeah.
Why do they want to get rid of the passenger pigeons? Why didn't people want them?
Excuse me?
Why did people not want the passenger pigeons?
Oh, they wanted them. You see, first of all, they wanted them because it's like free animal feed coming out of the sky, okay? So they mow them down and they use them as animal feed. Then some marketing guy comes along and says, let's convince the people in New York City that this is a delicacy to eat. And all of a sudden, every top restaurant in New York City is saying, the latest thing is passenger pigeon. They're shipping boxcar loads of passenger pigeons, barrels of them all over the place, to New York and other fine restaurants. Aside from that, you've heard the term stool pigeon, right? It comes from the passenger pigeon. You catch a passenger pigeon, you tie a string around its leg, and you tie the string to a stool and you sit it out in the field. The other passenger pigeons flying along say, oh, there's one of our friends down there. They say, must be food around it. They all go flying down, land on the field. Then you mow them down. That's where the term stool pigeon came from. Then they would try to catch them alive, and they send them to shooting galleries. The shooting galleries, we pick off, little shapes, right? People used to think it was a lot of fun to shoot the pigeons, the live pigeons. So half the people in New York are eating the things, the other half are shooting them. Yes.
Comment on the low probabilities.
Yes.
Daniel Kahneman, in his recent book, Thinking Fast and Slow, deals with the difficulty that most people have of estimating and dealing with low probabilities.
Yes.
In other words, they tend to recognize them, a 1% chance of something happening is treated as much larger,
Yes.
for example. I don't know if you
Yes.
encountered that.
I mean, we're not good at estimating these things. And we have to. I think we need to be objective in trying to calculate them as best we can, and act on those probabilities in an intelligent way. But we're not good at them. I agree with that.
I think we need to cut off the questions here. It's been very interesting. Thank you.